If an algorithm takes fn steps where f is a polynomial, we say the algorithm runs in polynomial time. However, it's possible for fn to be non-polynomial. For example, the binary search on n elements requires log to base 2 of n steps. But since the only requirement for being a complexity function is having an output a positive real number, any function could be a complexity function. For example, it could be a square root, an exponential, a trigonometric, as long as we take the absolute value. So where do these fit? Well, let's consider some limits. If Gn is order Fn, there are positive constants c and c prime which sandwich g of n between multiples of f of n for all sufficiently large n. Since we're assuming fn is always positive because it's a complexity function, we can divide by it to obtain, and taking the limit, while limits don't always exist, if the limit exists, it must be between two positive real numbers. And this gives us an important result. If g of n is order f of n, then the limit of the quotient is k for some finite positive k. Actually, this isn't useful. Remember, to use an if something, then something, you have to have the antecedent. So in this case, as stated, we have to know that g of n is order f of n. But that's usually what we want to determine. So what can we do? And so it helps to remember, consider the contrapositive. We have a statement of the form if something, then something. And so the contrapositive would be, if the limit is not a finite positive value, then g of n is not order n, again provided that the limit exists. Now, in practice, if we're dealing with complexity functions, then the quotient is non-negative. So the only way for the limit to exist and not be a finite positive number is for it to be 0 or infinity. For example, let's prove that log is not order n. So we find the limit as n goes to infinity of the quotient. And since the limit as n goes to infinity of log is infinity, and the limit as n goes to infinity of n is also infinity, we can use L'Hopital's rule, and we find and so we get a limit of 0, and so log is not order n. Let's do something more ambitious and prove that e to the n is not order n to the power k for any whole number k. Now, notice this is a statement of the form e to the n is not n, e to the n is not order n squared, e to the n is not order n cubed, and this is an ordered, infinite sequence of claims. So we should try induction. So, first, we find the limit as n goes to infinity of e to the n over n to the first. And again, since numerator and denominator both go to infinity, we can use L'Hopital's rule and find and so our limit is infinity, so the claim is true for k equals 1. Now, suppose it's true for some value k. In particular, the limit as n goes to infinity of e to the n over n to the k is infinity. Then, let's consider k plus 1. Our limit as n goes to infinity of n to the power k plus 1. We can apply L'Hopital's rule. K is some constant, so we can remove that factor. And we already know what this limit is, and so the result is also true for k plus 1, and consequently it's true for all values of k. Now, while this tells us what the order is not, what is the actual order? Let's take a look at that next.